Are we online? Okay, thanks, Guilherme. Hi, my name is Miguel Galante. I will be hosting this seminar today. So this is the first of a series of web seminars on behalf of CINE project. I'm glad to be the first one. I hope you enjoy it. And so each month, one of the divisions will present a literature overview or a seminar or some results of our work. And today we'll talk about the first division is ours, so it's the Dense Energy Carriers division, which is coordinated by Professor Ana Flavia. And I am within the project 4 in this division, which is coordinated by Professor Claudia Long. So I will talk a little bit about, mostly about the literature overview on this subject and a few results. Mr. Guilherme Brandini is here with me just to make sure that audio and video is okay. And yeah, so now we'll change the screen for the presentation, and you will hear me while we talk about this subject. And yeah, see if it works. Okay, so we'll talk about the novel materials for CO2 reduction reaction using solar energy. As we can see, just give an outline on what we'll be presenting today. We'll mainly discuss the literature and see that we have some issues regarding data presentation and data comparison. So these graphs, these two graphs are automatically generated by Web of Science. So we can see that if we look with not many filters in the search, but in general, CO2 reduction somehow induced by light, we see that we have lots of papers, so it recently attracted much attention. And we can see also that it's spread all over different fields of knowledge. So we have from chemistry to physics, from engineering to crystallography, and so on. And especially in the last 5 years, there's a lot of publication in this subject. It just became a hot topic because it's a really promising strategy to tackle CO2 levels using solar energy. So it's promising for a completely sustainable route for CO2 reduction, and we can also use carbon dioxide as a building block for interesting projects. And of course, it's really good to have lots of data to work with. But the thing is, since it's a relatively new topic in the literature, and since it's all over these different areas, sometimes it's really difficult to achieve consensus when you compare all of these data in the literature. And this is mainly because there's still not much protocols to present experimental data, for instance. But luckily, we have already a few, some really good review papers in the literature, and we will rely on these for this presentation. Just a brief description of this seminar. We will briefly introduce what is the photoelectrochemical approach for CO2 reduction. We'll find it in the literature as PEC CO2RR, so the photoelectrochemical CO2 reduction reaction. And then we'll give a literature overview and deal with these issues, especially when one is looking for activity data and especially selectivity data. So after that, we'll try to describe two important figures of merit that we consider when we evaluate photoactive materials for CO2 reduction, which are photocurrent and the surface absorption energetics. And then in the end, we'll talk just a little bit about the ongoing research in our group, specifically on silver-based oxide semiconductors. So this presentation is, of course, intended for the general audience, so especially students who are starting to work with CO2 reduction or other members on CINE project that want to collaborate with us and have some ideas. So, of course, there will be no major novel results to be disclosed today. So, I think we have one issue here. 1 second, Guilherme will help us here. Oh, okay. So, yeah, the first thing is that, as I mentioned, there's a lot of issue in this field of knowledge when you go to the literature. So we will find all of these terms in paper. So I got here some examples from really good journals, And you can see all of them. You can see photocatalytic reduction, you can see photoreduction, conversion under visible light, photoelectrochemical. So what is the proper terminology for that? And people sometimes think it's not an important issue, but it is. So 2 years ago, researchers from this field gathered in Hungary in the ISE meeting, and to discuss the current trends in photoelectrochemistry. And this terminology issue was actually one of the topics of debate. So as it's highlighted here, there are two really important things, so the proper use of terminology and metrics. And for instance, they mentioned that the term photocatalysis, when you talk about catalysis, usually it's actually a UPAC definition, right? So you are actually lowering the energy barrier of a kinetically hindered process, but it's a downhill thermodynamically process. And as we will see later, CO2 reduction is an uphill, thermodynamically uphill process. So terms like photosynthetic, photoelectrochemistry, or photo-driven, which is a more general term, might be more appropriate for this case. So, of course, if we are trying to convert CO2 into something useful, we are definitely defining thermodynamics, as we can see in this table below. Yeah, so just one observation, especially for students watching this presentation. There's a lot of text, of course, so you can watch it afterwards. The presentation will be available online, so you can watch again and pause and read everything properly. And also, all the figures and tables I'm showing, I'm putting the reference. So these are really good references to start learning about CO2 reduction. So back to the reaction, we can see in this table that we are defining thermodynamics. All the formal potentials for CO2 reduction to useful products are negative, which means a positive change in free energy, especially if we see the direct one electron transfer to CO2. If we couple this process with together with water, for instance, we can lower these hindrance, but it's still negative potentials. And you can also imagine that everything, all the organic matter in nature, sooner or later everything tends to go to CO2. So it's a thermodynamic trend. However, nature has also mastered the reverse reaction. So by means of photosynthesis, many organisms can convert CO2 back to useful things with remarkable selectivity, actually. But of course, nature has not exactly a rush on doing it. But if you want to let's say, to produce fuels from CO2 reduction in an industrial scale in the future, we need to be more, we need to increase the rate of this process. So by using semiconductors, which can absorb light, this is a promising strategy for CO2 reduction. And this is what we call the photoelectrochemical approach. So in a really simplified manner is what you see in the figure below. A photon, light will reach the semiconductor surface and will promote one electron to the conduction band, and then we can use, you see some examples of reduction reactions like hydrogen generation or CO2 conversion to methane and so on. So the photoelectrochemical approach is exactly what the name, it's exactly what the name means. So it's the conventional electrochemistry. So we'll have an electrode in solution, and then we'll promote a redox process in the surface, for instance, CO2 reduction. But it's photoelectrochemical because we are also using a semiconductor which can absorb light. So we combine both approaches as we have light as an additional energy input. And then, of course, we are using solar energy to produce useful molecules from CO2 reduction. So, as we are talking about semiconductors, we'll not get into defects here because this could be probably subject for another whole presentation. But semiconductor properties are mostly defined by, of course, the atoms that builds up this structure and the crystal structure, or in other words, how these atoms are positioned in space or in the unit cell. So these two features will give characteristics like band gap, charge carrier mobilities, or in other words, electrons and holes mobilities, and surface properties, of course, not only bulk properties. And these three characteristics, of course, will also interfere on actual on measurable parameters like electroactivity and selectivity or light absorption. So this diagram shows some examples of band structures of photoactive semiconductors. And this is really interesting, this figure, because sometimes in the literature you find valence and conduction bands just like a straight line or something like this. But this figure actually shows which atomic orbitals contributes to each band on each material. So this is really important because the major consequence of it is that depending on on which orbitals are contributing to this band, it will define also the reactivity and the behavior of these semiconductors and these electronic bands. And also, it should be noted that these bands are not randomly located in space. We actually have an energy scale. So a band diagram always need an energy scale. So the students that want to work with that always look for that. Sometimes the bands are showed without an energy scale, but this is kind of meaningless. We need an energy scale. For instance, this one is regarding to the hydrogen electrode. It can be vacuum scale or some other scale, but it's always important to have a scale. And not only to, where the bands are located, it's usually referred at the band position. And this is important not only because of the band position, but any chemical reaction or any other, any redox processes can be also placed and located in this energy axis. And this is what usually I'm a chemist, so we call it the chemical potential, and people from physics call it Fermi levels, but it's pretty much the same thing. You can locate redox potentials in the same energy axis where you locate the band positions. So remember that we are interested in using electrons which are promoted to the conduction band to work with reduction reactions, right? So if you have this information, you can know at least if the electron in this conduction band will have enough energy to promote this reaction. Or in other words, you can at least know if it's thermodynamically feasible to achieve the desired process instead of just making trial and error steps. And of course, as you can see in the diagram, in the full diagram, depending on the atoms and depending on the orbitals composing these bands, you can change the band gap or the band position or the band reactivity. So all of this is usually referred in the literature as band tuning or band engineering. So, and you can change all of this in the right-hand side, the box with 6 measurables. We'll now just discuss a little bit about 2 of them, the activity and selectivity for CO2 reduction. So recently, actually, this is a really good review paper. It's specifically for CO2 reduction, but it has a really good introduction on the basics, on the fundamentals of semiconductor photoelectrochemistry. So it will I definitely recommend everyone to get this reference. It will talk about banding, Fermi levels, and the role of defects as well. So it's really good to learn the basics of photoelectrochemistry. So this here it's still for metal electrodes. We are not talking about semiconductors yet. And this is really beautiful. It's a selectivity map using the periodic table. So this might be a first thing to do if you are looking for materials to convert CO2. And it's really, well, of course it's kind of disappointing if you want to work with metals, that most of them has the tendency to produce hydrogen instead of CO2 reduction products. And also really interesting, copper, it's really interesting that it differs from others. It has a remarkable selectivity for hydrocarbons. And if we want to make a similar map with semiconductors, we need a solid data. We need solid data from the literature, and it needs to be comparable. It needs to be comparable to each other. But unfortunately, that's not what happens. So, the main issue here is that, and now this is another paper from Alexis Bell group, where they try to, this is from last year, a really good paper, and they try to present some protocols to report CO2 reduction data. And I recommend to go for everyone to go through this test, but to make things simpler, the idea is that you have much more variables than what actually seems when you are working with CO2 reduction reaction. So a practical example, let's suppose you have a conventional electrolysis cell like this one on the right side, and you will try to run a CO2 reduction electrolysis experiment in your lab. So of course you will check you are used already to use your own setup, and then you will check you'll make like a checklist, right? So of my electrode is well characterized. I know what I'm working with. Good. I have a good temperature control. This is really important. My potential stat is calibrated. It's good, and I have already calibrated my I don't know, a GCNS or an HPLC to quantify products. Great. So we're good to go. So in my, let's say, in your opinion, in your lab, you will run the experiment with everything under control, and any other group who try to repeat the same experiment will have the same results. But unfortunately, that's not that simple as they describe in this paper. There are many other variables that must be kept under control. So for instance, different crystal facets, cell hydrodynamics, for instance, using steering or not, and even the rate of steering, the speed of steering. And the electrolyte, if you use, let's say, sodium sulfate and someone else uses sodium bicarbonate, the selectivity might be really different. Changes in the surface, like corrosion, and the surface area. All of these must be presented together with the final quantification result of CO2 reduction products. Otherwise, comparison between experiments in the literature are likely not to be reproducible. So, and note that we are not talking about semiconductors or photoelectrochemical reduction. If we put light on the system, it would be even more complicated, of course. Light adds significant complexity. And then in this case, I recommend this. This is a really very recent paper where CO2 photoelectrochemical reduction is discussed. And the authors present a list of review papers. And most of them, as we saw in the beginning of this presentation, most of them are from last probably 6 or 7 years. So, but again, if we go through each of these reviews, we will see, of course, this is not any fault of the review authors, but we will go into this issue of different data protocols for presenting, and we can check another practical example. Let's say then tomorrow we need another material for a solar fuels facility, and then we'll go to the literature and check. Of course, we are going to a high impact journal and have a good review paper, and then we will try to decide on which of these materials we would like to use. So let's say specifically for these two materials I've highlighted, and notice that this table explicitly it calls itself a performance table. So let's compare these two materials. So we have it's probably two core shell structures, non-structured particles. So the first one is manganese oxide with titanium dioxide and a copper platinum alloy. And the second one is titanium dioxide decorated with silver. So if you just look at this table and try to get some conclusions, first reading, what you would say? Well, the first material looks more active because it generates 84 micromoles per hour per gram of CO2 reduction products, while the second one, it's less than 2 micromoles. And you would also say that probably the first one is selective for CO, while the other is selective for methane. These two conclusions, based specifically on this data, if right, they would probably be pure luck, because this data is not, it's far from being enough to make any conclusions. And these are the reasons. Well, the first one, as you can see, uses sodium sulfite as a sacrificial reagent. Well, if we are talking about the object of study CO2 reduction, if you put a sacrificial reagent, which is a quite common practice to try to increase the activity of the efficiency, the overall efficiency of the system, well, it's a good strategy to increase product formation. But in a practical sense, if we remember that our practical example is selecting a material for an industrial facility. So there's no point in using a sacrificial reagent. And of course, the activity will be higher if you use one. But you pretty much change the whole thermodynamics of this system. Also, and this is why light adds lots of complexity. The first work uses one sun as a light source parameter. So one sun, it's pretty much what the name means, the full solar spectrum from a solar simulator, while the second one uses a cutoff filter, as you can see, lambda higher than 420 nanometers. And this is actually odd, because TiO2 band gap is in the UV region. So of course, if you cut off the whole UV region, you have a decrease in photoactivity. And finally, and extremely important, all of these performance, or almost all of them, are normalized by mass instead of active area. And of course, mass would be important if you are thinking in an economical aspect, but in a catalysis sense, in a catalysis point of view, surface area is always important, because it's a direct measurement of the amount of active sites that you have. So there's not much sense in normalizing these data by mass, in our opinion. So I also present here another review paper. It's from this year. It's a really good paper where the authors explain how to properly obtain the electrocatalytic area, or the electroactive area, which is the important parameter for us. By looking this slide so far, it looks pretty much that we don't have, there's no way of using data from the literature, but that's not true. Of course we can, but we do believe that just relying on activity measurement data or product quantification would mislead you in your choice of photoactive materials. But there are what we call figures of merit to actually evaluate semiconductors from the literature. And the two, there are many others, but we'd like to discuss two of them, which are the photocurrent and the surface absorption energetics. So the photocurrent is simply how much the current density increases when you illuminate the electrode. And of course, this is related on how much electrons you can transfer to the solution, and of course, how much CO2 you can reduce. And this can be assessed by electrochemical experiments, by electrochemistry. And the surface absorption energetics is how strong and what geometry CO2 absorbs to the electrode surface. And this completely defines the mechanism, not only the activity, but the mechanism that CO2 reduction will follow. And this can be probed by mainly by computational techniques, and also with some in situ techniques. So there's, again, a lot of text in this slide. You can go back later and read it and pause and take your time to read it. But the photocurrent is defined by the Butler-Gardner model, which derives this equation. So these two scientists, back in the 50s and 60s, they provided a deep insight on how photocurrent is generated on semiconductor surface. And the main conclusion is that charge carrier generation does not take place only at the very surface or the interface of semiconductors, but it actually goes into the bulk, mainly in the space charge region. Actually, all the charge carrier generation takes place in the space charge region, or a depletion layer or an accumulation layer, depending on what semiconductor you are using. And it can give you some intrinsic information like the space charge width or the flat band potential of our semiconductors. And specifically for reduction process like CO2 reduction, we need to transfer electrons into the solution. So we need materials that accumulate electrons on its surface, and for instance, in the interface with water or the electrolytic solution, it must accumulate electrons instead of holes. So this would be attained by using p-type semiconductors. So it's really important when you are looking for semiconductors for CO2 reduction reaction, they need to be p-type semiconductors. Or in other words, holes are the majority charge carriers, the charge carriers with higher mobility. And just to talk a little bit about the photoanodes, the reader will probably, the viewer will probably note if you go to the literature that there are much more, there are many more publications for N-type semiconductors or photoanodes, and they systematically present higher photocurrent. And the main reasons for that is that N-type semiconductors are more stable, so they are definitely easier to work with, like titanium dioxide and tungsten trioxide and so on. The photo current is higher because it relies on electron mobility instead of hole mobility. And for photoanodes, it's really common to find reports of photocurrents higher than 1 milliamp, or even sometimes 10 milliamps or even more. But this is not that usual for photocathodes. So if you are working with a new semiconductor and you can measure photocurrents, a few hundred microamps. It's not supposed to be milliamps in the last sentence. But, well, if you have a p-type semiconductor with a photocurrent of a few hundred microamps, this is quite good already. So, and you should consider that for CO2 reduction. So let's see some, really quickly here, some examples from the literature. For instance, copper niobate. And here we are only talking about metal oxides, which is it's what we are interested in. So 250 microamps for copper niobate, though the authors also mentioned that there is some photocorrosion. So it's expected to have only copper 2 in this compound, and after the experiments they see some copper 1 and metallic copper, so this is definitely a photocorrosion. But the photocurrent in this material is remarkable. We also have this one. This one is really interesting because it's only based on earth-abundant elements, so it's probably a cheap material. And these photocathodes also show photocurrents up to 1 milliamp, so this is really good for CO2 reduction. Again, some photocorrosion observed by the formation of metallic copper domains. Though some authors actually, let's say, like it because metallic domains can increase the electrocatalytic activity of a semiconductor. And here we also have another copper-based compound. So this is really interesting, a hierarchical structure of copper 1 oxide and tungsten oxide, and which is able to generate methanol as CO2 reduction product. And copper oxide and titanium dioxide, another interesting material, photocurrents up to 1 milliamp at a really low overpotential, so this is a really promising material. And finally, this is not exactly for CO2 reduction, it's for hydrogen evolution, right? So for proton reduction. But it's pretty much the same thing that we're looking for. But the interesting thing here is that it's a silver-based complex oxide, and it is shown that the photocurrent for this material it's much higher from its copper counterpart. So silver oxides are also really interesting, and they are usually more stable than copper-based oxides in photoelectrochemical conditions. So after checking all of these examples, the viewer probably noted some things in common. For photocathodes, copper and silver oxides are preferred, so they are the most studied materials. And there are, among many reasons, these metals with D10 configuration, the oxides of these metals, they have really high conductivity and they tend to be a p-type, and that's what we want. And they usually also have a really good light absorption property. However, their native oxides, so silver oxide and copper 1 oxide, they can't be used because they are really unstable, unfortunately. We've tested, we worked with this material already, so it's really common material you can test in your lab. If you make an electrode, let's say, based on copper 1 oxide, the pure oxide, you will see a huge photocurrent, but it will last for probably no longer than 5 minutes, let's say. And we will check the electrode, and it's all black. It's all corroded. So these materials are prone for photocorrosion. And you may also notice that copper 1 oxide oxides in general are preferred over the copper 2 oxide, and that's why the conduction. The reason for that, the conduction band is higher for the copper 1 oxide, so the redox power of the electrons promoted to this band is higher. You will probably find other materials in the literature with higher photocurrent, sometimes plasmonic compounds or sulfides and phosphides, but oxides are really simple to work with. They are cheaper, so this is why we highlight results based on oxides, metal oxides. Well, the second figure of merit that we mentioned before is the surface adsorption energetics. So we're pretty much asking how CO2 adsorbs in the semiconductor in terms of geometry, how strongly it adsorbs, and how strongly the products of CO2 reduction reaction adsorbs or desorbs. Well, so the thing here, this is extremely related to selectivity. So the first step in CO2 reduction is transferring one electron. It could be coupled with water or not, but it's mainly transfer one electron to the CO2 molecule. And it's really different whether it really makes a difference whether this molecule is in the linear or bent configuration. So as stated in this review, it's also a really good review on theoretical insights into CO2 reduction. So the more bent the absorbed CO2 is, it will be easier to transfer the electron to the lowest unoccupied molecular orbital. And this is really important. We can see in this practical example, a recent paper on PCCP, where the authors try to evaluate how CO2 absorbs on titanium dioxide surface. As we can see, so we have one possibility for linear absorption, which is figure A, and two possible band conformations. So we can see, well, these energy values in electron volts, it's the absorption energy. So the more negative they are, the more favored the conformation will be. So we can see that the absorption energy for the linear conformation, it's much more negative or more favorable, which of course will mean that the surface of the semiconductor will be mostly covered by an inactive form for CO2 reduction. So this will not be a good surface for CO2 reduction. However, when you add a copper cluster or copper atoms to this surface, this tendency is now the opposite. So the bent conformation has now a more negative absorption energy in this surface. So it is expected from these results that CO2 reduction will be more efficient if you add copper to the titanium dioxide surface. We have here a note again that we are always talking about copper compounds. They tend to be definitely the most active for this reduction. But the computational approach can also provide absorption energies, not only for the actual CO2 molecule, but also for the intermediates. So you can propose many reaction intermediates and calculate, like this work here on ACS catalysis. You can calculate the energy, the absorption energy of different intermediates on different crystal facets, on different potentials. So this is a really powerful approach to study this reaction. And if we just look for all these tables and diagrams and schemes, this just probably looks like a lot of data, but the actual, the beautiful work is to rationalize all of this data and provide what is shown also in this work, which are these selectivity maps. This is definitely something amazing in CO2 reduction. So some authors call it selectivity maps or roadmaps or pathways. And we can see I think the resolution in the presentation might be not really good because of the broadcast, but the video will be, you can go to the reference also and see these maps. So you can see for each, the authors were able to calculate for each copper crystal plane, crystal facet, absorption energies and energy barriers for several intermediates. And using these roadmaps, one can predict if a material would be selective, let's say, for instance, for methanol, or for hydrocarbons, or for multi-carbon compounds, alcohols, and etc. And this is really becoming a thing in the literature, in the recent literature. And for this other paper also worked with this kind of roadmaps for multi-carbon compounds. And you will notice that the actual starting point for this simulation, for this calculation, is not CO2 itself. Usually these intermediates, so the carbon bound to the substrate by a single bond, and carbon with a triple bond with oxygen. This is usually this is the most common intermediate for this simulation. And this is because after that the reaction follows a very similar pathway to carbon monoxide reduction. And this is a well-known studied reaction, both CO oxidation and CO reduction. It's been studied already for many decades. And yeah, so again, another example of this roadmap. And finally, these calculated mechanism, this proposed mechanism can be probed not only by quantification techniques in electrolysis experiments, but also by in situ techniques like Raman, X-ray absorption, infrared absorption, or even mass spectrometry online coupled with the photoelectrochemical system. And this is what we can see in the most recent literature. A mechanism is proposed by the computational approach. It is probed by an electrolysis experiment and followed by an in situ technique. And we have some examples to show here. For instance, this paper here on nature catalysis. So this will be pretty much what we mentioned before. First of all, okay, DFT suggests that this alloy and adding tin to the tin copper alloy would favor formic acid. It is observed in the electrolysis experiment, and so it confirms the expected trend. And the in situ techniques, in this case X-ray absorption, can provide further insights. Or this other one, well, the author has a material with remarkable photocurrents, so it's worth testing. Calculations predict selectivity toward alcohols, and the electrolysis confirm the expected trend. Well, another example, the reaction pathways, the calculated pathway indicates that the barrier for formic acid formation is lower. The selectivity is observed again in the electrolysis experiment, and it's also followed in this case by in situ Raman spectroscopy. So before briefly talking about our results on silver oxides, just what I'm trying to convince the audience. As a recent topic, we have a lot of data in the literature, and many authors publish the electrolysis experiments result. But if you want to start to work with CO2 reduction, if you guide yourself by activity measurements just for electrolysis experiments, this can be misleading. And this is because of the lack of experimental protocols. Photocurrent is a more reliable figure of merit because a photoactive material will be photoactive no matter if you use different electrolytes, let's say, and surface area, things like this. So photocurrent is a reliable figure of merit. And surface absorption it's also really important, especially if we want to predict selectivity trends. And yeah, so this is the state of the art. It's combining the computational chemistry, the electrochemistry, and the in situ techniques. So the ongoing research in our group, we are actually doing lots of stuff here, but I will focus only on silver oxides. And oxygen, this is a really common diagram to find in the literature. It's provided by the United States Geological Survey, and what is shown here is the elemental abundance of each chemical element on Earth's crust. So of course, oxygen is the most abundant. So if we combine it with metals, of course, it's an interesting approach in terms of cost, but also in terms of stability. So we know that sulfides are also really good. It's a promising class of materials, but the stability is still an issue, especially if we're working in aqueous solution. During photoelectrochemical experiments, sulfides usually suffers from photocorrosion. So we recently published a review on Electrochemical regarding silver complex oxides for solar energy conversion for photoelectrochemical processes. And as we mentioned before, silver oxide, it's really good because it's a p-type semiconductor. It has a really narrow band gap and extremely high electrical conductivity. However, it's impossible to use it in its bare form in photoelectrochemical systems because, unfortunately, it's really unstable. It suffers from photocorrosion. However, if we combine silver and oxygen with different metals, we can, so the idea in this review paper was to explore the phase diagrams of the system and try to find some trends in terms of photoelectrochemical properties. So, for instance, we can work with two elements plus oxygen. So, silver and silicon, we can see that the increasing amount of silver, we can see a trend in the upshift of the valence band. And this is actually observed, we deal with many other examples in this paper, in this review, and we can also see the same trend. Now we have a quaternary system in a ternary phase diagram. So we have three, we call it quaternary because we have three metals and plus oxygen. So it's silver, bismuth, and tungsten. And we got really interested in this silver bismuth tungstate, AgBiW208. So we've worked a lot already with this compound. So we recently published this paper on JPCC, where we evaluate this AgBiW208 phase as a promising photocathode. So we can see, for instance, that if we compare with bismuth tungstate, which is an N-type semiconductor, we don't have cathodic photocurrent for bismuth tungstate, but for the silver bismuth tungstate, we have a remarkable photocurrent. And we also evaluated this multiphasic compound. So we tried to synthesize this material by hydrothermal synthesis. I'm not going into experimental details. You can check the paper for that. But we synthesize a multiphasic material. So we have in the same compound the quaternary phase, which we call ABW here for simplifying. We have also bismuth tungstate together and metallic silver nanostructure domains. And we evaluated this compound, and we used, for this work, well, these electrolysis experiments are not published yet, so I'm just disclosing a little bit of what we are doing now. We are running electrolysis experiments using imidazole in the electrolyte, which is known to be an electron transfer agent. This was first presented by Professor Andrew Bocarsley from Princeton University, and imidazole seems to be a promising approach to convert CO2 because it transforms CO2 from its linear conformation to its band conformation. And this mechanism using imidazole is supposed to be selective for formic acid. So we synthesize the multiphasic compound, the material without the silver domains, and the pure phase ABW. And what we see is that when we evaluate the liquid phase after the electrolysis experiments, for the pure phase we don't see nothing, but the compounds containing the heterojunction, bismuth tungstate, silver bismuth tungstate, we see formic acid production induced by light. So this indicates that these two samples undergo CO2 reduction reaction following the imidazole mediated mechanism. However, when we analyze the gas phase product, we see that the pure phase is selected for CO formation or again induced by light. While the other compounds, the one together with bismuth tungstate, it only forms trace amounts of CO. And the multiphasic compound can form CO as well, most likely because of the metallic silver domains. And we see, so to summarize all of these results, this is what we see. So pure ABW is selected for the direct reduction of CO2, while the heterojunction undergoes the mechanism mediated by imidazole. And so here we work with this AGBI W208, and we also try to synthesize this material using a different technique, so a melting technique. And it's really interesting that we actually got a novel, a new polymorph of this with this composition. This was really, we were really surprised by that. We reported this novel structure in a paper this year, and now just to finish, because I'm actually almost out of time, just a preliminary result for CO2 reduction reaction using this novel phase. So we can see in the cyclic voltammetry analysis that it is electroactive for CO2 reduction. If we compare the system with and without CO2, we can see some additional reduction peaks and also a reoxidation peak in the reverse wave. So this is really interesting. It's it means that we have reduction products adsorbed to the electrode surface, which are reoxidized when we go to the reverse wave. And we also see that it's photoactive, so it's also p-type. We see in the cathodic sweep that the current is increased when the system is illuminated. And if anyone else on CINE project is interested in oxygen reduction reaction, this material looks really promising, looks really active for the electrocatalytic oxygen reduction reaction. We haven't gone into much details yet for this reaction. We haven't checked if it's peroxide formation, but it's definitely on the plans. So to summarize these results from our group, we present some results with this silver complex oxides. We can work with the hydrothermal synthesis, which provides the multiphasic compounds. We can also use the melting technique to have the novel beta phase. And working with this phase, we can tune the selectivity towards carbon monoxide or the formic acid formation. And what we suggest for as next steps, we can do a lot on using computational aspects to actually evaluate the band structure and the charge carrier mobility on these compounds, and also, of course, the CO2 absorption energetics. And we can run electrolysis experiments using in situ monitoring. Actually, our group and Professor Pablo's group, we already have really interesting results using in situ infrared spectroscopy. And well, for CINE members, there's much more being done. We are working with copper oxides. We are working with bismuth oxides. We are working with polymers. So if you all want more details on the ongoing research, please contact us. And this is it for this presentation. I hope you like it. I would like to acknowledge the CINE project and also the University of Campinas and the Campus Institute. Thank you all for the audience. If you have any questions or suggestions, please contact me. You can email me anytime you want to ask your questions. So our transmission is finishing, and I hope you all enjoyed. And you can feel free to email me. And next month, Division 2 will present the next web seminar. So stay in touch with CINE channel for the monthly web seminars. And again, thanks for your audience.